Grade 12 Physics, Light Note number 3, Young's double slit experiment. In this note we're going to look at what an interference pattern is and what we need to create it. An interference pattern is something that's only created with waves. This was shown by Thomas Young back in the 1700s. On this first page of the note we're going to show what essence or what conditions we need to make this double slit or to make this interference pattern, and this can be done using water waves, light waves, sound waves, any type of wave you can think of. Well, first we need some barrier with a single slit through it, and behind it will be a barrier with a double slit. Let's say some waves go up and meet that single slit. The waves will permeate out, they'll diffract, and they'll bend around looking like a puddle. As they move away from that single slit, they're going to hit both of those double slits at the same time, where again they're going to diffract. The two waves through the double slit, as they interfere with each other, that's what will produce our interference pattern. This is only possible if the light coming through is monochromatic, meaning it's all of the same frequency, or in light's case it's all the same color, and those waves have to be in phase, so they have to be going up and down at the same time. So let's look a little more closely at the wave interference. Here we have waves coming through a double slit. Each line is a crest, so we can note on this interference pattern, or where we can note where crests are meeting crests. These are going to be spots of constructive interference. As we label them, we get to see that there's actually a pattern occurring. The crests all seem to be happening in a line, and if we trace that line out, it's going to hit the screen at a particular spot. So if this is light, crests are meeting crests, we're actually going to get a bright spot on the screen where these locations are. We call these bright spot fringes. On the other hand, between the bright spots, we're going to get a dark spot on the screen. This is going to be complete destructive interference of the light. We call these dark spots nodes. So what an interference pattern is if we put a screen beyond the double slit, we're going to see an interchanging pattern of bright spot, dark spot, bright spot, dark spot. That's what an interference pattern is called. If we actually look at the intensity of the bright spots, or how bright they are, we can see that the middle one is the brightest, and the brightness actually decreases a little bit as we get further and further from that middle spot. Let's start to look at what's actually happening for light to interfere to make that middle spot. Here S1 and S2 are going to be the paths that light's going to take through the first slit or through the second slit. If we look at a particular wave going through each of the slits and hitting that middle fringe, we see that there's no difference in length or no path difference going through slit 1 or slit 2 to get to that middle spot. It's an isosceles triangle that gives us perfect constructive interference. If we actually start to look a little higher, let's say we look at where the first fringe occurs, S1 is not going to travel as far as S2 does. The total distance that S2 travels is a little further. So for the creation of the first fringe, the path difference between S1 and 2 ends up being 1 lambda. That means S2 travels a whole extra wavelength compared to S1. In this case, if that happens, we still get constructive interference and we get that fringe created. If we change the angle a little bit and actually look at the node between the two fringes, here, if we look for the creation of this node, the path difference between S1 and S2 ends up being a half lambda. So that means S2 only traveled half a wavelength more than that top S1. This is what produces the destructive interference. So let's look at some of the math that creates our ability to calculate where fringes and nodes occur. So looking at a similar diagram here, let's just pick some arbitrary angle from this double slits. Here we're going to pick an angle that goes up to that first fringe. If we take a look at the path difference of that first fringe, we know from the last slide that it's 1 lambda. The path difference to the second fringe will be 2 lambda. If we went to the third fringe, it would be 3 lambda. So we can say that for a fringe, the path difference will be some multiple of lambda, or n lambda. Alternatively, if we look at the nodes, we know it was a half lambda wavelength to get that first node, 1.5 to get the next node, 2.5 to get the third node. So we can make a general statement here that the nodes, the path difference, is going to be n subtract 1/2 lambda. If we zoom in where the double slits are, there's going to be some separation between the double slits, which we call D. And we know that S2, that second path, traveled a little further than the top one, so that's going to have a path difference. That path difference, the bottom part of that triangle, is equal to d sine theta. So d is the distance between those slits times sine of the angle. So therefore for fringes, the path difference, if we equate both of those equations, is going to be n lambda equals d sine theta. And for nodes, we're going to, if we equate the equations, we're going to n subtract 1/2 lambda equals d sine theta. So there's two equations here. One that gives us the ability to calculate where the fringes should be. The other one gives us the ability to calculate where the nodes should be. Sometimes it's difficult to measure theta whenever we're talking about a double slit. So if we look at the grand picture here, let's say we choose to measure some to the first fringe. It's going to be on some angle theta. We can relate that angle theta to the distance that fringe is away from the middle fringe and the distance that the double slits are away from the screen. Here, D will be the slit distance in measured in meters. L will be the distance of the screen measured in meters. XN will be the distance to the nth fringe or node. So if it's X2, it would be to the second fringe, or if it's X3, it would be to the third fringe. Therefore, this is a right angle triangle. So we can just use tan theta equals xn divided by L. Let's do one example here. Let's say we shine some light onto a screen. We don't know the color, so we want to calculate its wavelength. We're shining it through a double slit, so it's going to make some sort of interference pattern on the screen. The slit distance, or the distance between the two slits, is going to be 0.3 millimeters. The distance between the slits and the screen is going to be 1 meter. And if we measure from that middle fringe to the second fringe, it's going to be 4 millimeters. Let's determine the wavelength and the color of that incident light. Right? If we know the wavelength, then we can reference that with a color. If we have x2, that means n is 2. Let's first calculate theta. So we're going to use our equation above. So when we put the numbers in, we should get theta is equal to 0.229 degrees. Now we can use that in our fringe formula, where we're going to calculate lambda. First we need to rearrange it. Here we find that lambda equals 600 nanometers, which ends up being orange light.